All right, lesson 27, sadly, is like one of our longest sections. I will definitely break it into two sections next year, so I'm going to record it in two videos this year. But no worries, everything after section 27 is a breeze. So once you get through section 27, you are uh, on the way home with pre-calculus. Okay, so we're going to talk about polar coordinates today. Polar coordinates are really cool. So they allow you to graph some really interesting things, like you can see in your notes. So we have something called a lemniscate, rose curve, Archimedes spiral. So we have really cool graphs, but they also make some operations a lot easier for us. So for instance, if we easily want to talk about distances from the origin in all directions, maybe we want to use polar coordinates. So they will be very useful to us, just like everything else that we've learned, vectors and so on. And they look really, really cool when you graph them with your calculator. Okay, so let's start with the basics. So every point in the polar coordinate plane is given by r theta, where r is the distance from the pole, which is really like the origin in rectangular coordinates, and theta is the direction you want to go towards. So I made a big mistake on my notes, and when I drew these graphs, or I copied this graph in for you, I didn't realize that I had 15 degrees and 75 degrees as well. So really, like as you're graphing, only pay attention. Oops, see, I still messed it up. I always want to make that pi over 6. Only pay attention to the three lines right here in the middle. So pi over 4, pi over 3, and pi over 6. Okay, so ignore the 15 degrees and the 75 degrees. And on your test, I'll make sure that I don't even put those on there because it is kind of confusing as we're doing this. Okay, so what we're saying when we say 5 comma pi over 4 is we're saying along the line pi over 4, which is right here, we are going to go out 5 units. Okay, so this is a radius of 1, this is a radius of 2, a radius of 3, 4, and then 5. Okay, so the point that we want to graph goes along here, and then it goes out 1, 2, 3, 4, 5. So it would be right there. Okay. So if I do negative 3 pi over 6, I'm going along the pi over 6 line, which is this line. And I'm going to go actually in the negative direction. So I want to extend my pi over 6 line in the negative direction, and I'm going to go out 1, 2, 3 in the negative direction. So I'll do a big point there. So that's going to be right 1, 2, 3, right there. Okay, and then if I have 4 and negative pi, this is where it starts to get a little tricky once you get the negative angles. All right, negative pi, we know, is here, just like pi. So negative pi is the same as going pi. All right, then I'm going to go 4 out along that line. So 1, 2, 3, 4. It's going to be that line, right? Or that little point right there. So it's kind of hard for me to show this to you on the video without drawing those original lines. All right, then if I have negative 3 pi over 2, oh man, this is really getting tricky. Now we need to go around here to the negative 3 pi over 2 line. And we're going to go negative 3. So we actually go away from the line in the opposite direction. So 1, 2, 3, it's right there. Okay? So it's a little bit tricky when you're first learning these. And it's actually, there's a lot of ways to name these points, right? So like this negative 3 comma negative 3 pi over 2, why couldn't I just name it 3 and then 3 pi over 2? Why couldn't I do that? Well, you can. So that's the kind of frustrating thing. So there's multiple ways to name a lot of, like most of these points. So if I have 0 comma pi, I go out in the pi direction, but I only go out 0, so it's actually still just the pole or the origin, as you're used to calling it. All right, and then 3 comma 0, that means I go along the 0 line, and I'm going to go out 1, 2, 3. So it's right there. Okay, so don't get confused. A lot of people will see like 3 comma 0, and they think it is the rectangular coordinates. We are talking about polar coordinates, so we're going along the 0 line. Or like 0 comma pi. Some people will try to graph 0 and then up pi, right? Don't do that. Okay, so the second number is telling you the angle that you're going along, and the first number is telling you how far you go along that angle. Okay? So if I have negative 1, negative 5 pi over 6, 5 pi over 6 is going to be this line. See, I'm telling you, it's hard with these extra lines in there. And I'm going to go negative 1, so I'm going to go right here. All right, and then 2, 11 pi over 6. So 11 pi over 6 here. So I'm going to go 1, 2 right there. And then -3, -pi, I'm going to go, so here's the negative pi. That gets tricky with the negative pi. And we're going to go 1, 2, 3 this way. So 3 is right there. Okay, so like I said, I mean, in the end, you just want a single point. So if you lightly draw those lines and then kind of erase them, sometimes it helps. Okay, so name 3 different polar coordinates that represent the point 3, 5 pi over 6. So if I'm doing the polar coordinates and I don't have any paper, or any graph paper like already set up for me, polar coordinate paper. And you can always download that online, polar coordinate paper. Here's a radius of 1, 2, and 3. So we're going to go 5 pi over 6 and then 3. 1, 2, 3. It's right there. So how could we name this? So let's stick with +3. But let's do a negative angle. So it would be -7 pi over 6. But what if I had a -3? If I have -3, then I could go along this line right here, which is 11 pi over 6. So I go along the 11 pi over 6, but I go in the opposite direction, right? And what if I have a -3 and I do a negative angle? Well, then it would be the -7 pi over 6. So it's kind of confusing doing the different forms. So there's actually 4 different versions of each point. So well, except for the zeros. Sometimes the zeros are weird, right? Only 2. But you can do like a positive or negative for the R value and a positive or negative for the angle as well. All right, so find the rectangular coordinates that correspond to the following polar coordinates. So if I have 3, pi over 4. So let's think about what that is. So I would go out along the pi over 4 line, a radius of 3. 1, 2, 3. So it's right there. So I want to know the rectangular coordinates. In other words, the x and y values. So I want to go out and up a certain amount. Well, this is 45 degrees, and we said that our radius is 3. So I want to find those other measurements. Okay, so the easiest way to do that, I mean, use a 45, 45, 90 triangle is actually the easiest way. So it's 3 over √2 and 3 over √2. But an easy way to think of polar coordinates is to always do r cosine theta and r sine theta. Because we've talked about this before with vectors. If I make this x and this y, if I want to find x, I can set it up with SOHCAHTOA. And I can say cosine of 45 degrees equals adjacent over hypotenuse. So I get 3 times cosine of 45 equals x. Well, what is that? That's my r cosine theta. Okay, so that's all I'm doing. So r cosine theta, if you do that, you're going to get 3 times cosine of 45, which is √2 over 2. And then I'm going to have 3 times √2 over 2 for the sine as well. That is the same if you were wondering 3 over √2 if you rationalize, right? You do get 3 √2 over 2. All right, so next one, 5 and 5 pi over 6. So if I go along the 5 pi over 6 line, I'm going this way, I'm going out 5. Okay, so it's right there. But again, it's just using those formulas that I just talked about. So what I'm doing is the r cosine theta and r sine theta. Okay, you could easily see that you have a 30, 60, 90 and do it that way as well. It doesn't matter. So if you wanted to do half, 5 over 2, and then multiply by √3 over 2, you can. Or multiply by √3, I guess. Okay, so anyway, so your answer, if you do 5 cosine of 5 pi over 6, I'm going to have 5 times cosine of 5 pi over 6 is negative √3 over 2. Let's see, I forgot my negative when I did that. All right, and then this is going to be 5 times 1/2. So I'm going to have negative 5 √3 over 2, comma, 5 over 2. All right, now 3 pi over 2, these are the easy ones when they're on the x or y axis. They're not really x or y axis, but you get what I'm saying. So I'm going to go out 3 in this direction. Okay, so what point is that in rectangular coordinates? It's 0, -3. That's all you need. All right, and then 10, 5.2, there's really no nice way of doing this. This is 5.2 radians. So I would just use your calculator. So you're going to do 10 cosine of 5.2, 10 sine of 5.2. So when you do that, you should get 4.685, negative 8.835. All right, so the next part says find the polar coordinates that correspond to the following rectangular coordinates. I always want you to think about the quadrant. Does your angle make sense? If not, you have to change your theta around. So we've done this before with vectors. So if I have 2, negative root 2, okay, that means I'm going to go out root 2 and I'm going to go down root 2. So I need to find my r and my theta. So basically I need to find this distance, that's my r, and I need to find this angle, which is my theta. Okay, this is a very easy one to do without writing any formulas at all, right? I know that it's negative 45 degrees, so I'm going to call it 7 pi over 4. And my r, if I want to find that, right, it's a 45, 45, 90, so I can multiply by root 2. So root 2 times root 2 gives me 2. I could also do the formula, the square root of square root of 2 squared plus negative root 2 squared. And that gets it for me as well. All right, so my polar coordinates then are going to be r comma theta, so 2 comma 7 pi over 4. All right, same idea for this next one. So I have root 3, and then I have negative 1. This is also one of my special right triangles. So if you recognize that, go for it. If not, then we need to do a little bit of work. And we basically use those same formulas that we had for vectors. That's why these chapters are so close together. So I have x squared is root 3, and then I'm squaring it, plus negative 1 squared. So I end up getting 2. And then if I want to find theta, I do tangent of theta equals my b value, or my y value, over my x value, right? So tangent of theta equals negative root 3 over 3. And if you find that, you could find it in degrees if it's easier for you using your calculator, or you could notice that it is one of the ones that you should know from your unit circle. So this ends up being like 30 degrees, so it's 11 pi over 6. So your polar coordinates are r comma theta. So 2 comma 11 pi over 6. All right, the next one I just have 0 comma negative 7 root 2. That means I go down negative 7 root 2. So my radius is actually just the distance 7 root 2, and my theta is 3 pi over 2. So that's all you need, so r comma theta. So that was one where you didn't really need to do the work, you could just see it. And then this one's a little bit harder. It's not a value that we actually know from our unit circle. So we're going to use our calculator. So we're going to do r equals the square root of negative 3.5 squared plus negative 1.2 squared. So I end up getting r equals 3.7. And then if I want theta, I'm going to do tangent of theta equals opposite over, well, it is opposite over adjacent, but the y over the x. So when I put this into my calculator, I got theta equals, gosh, did I write it in radians? I think I got 0.330. Now that's confusing because a lot of you guys don't really totally understand what a radian measure is. So knowing where 0.330 is a little tricky. Just remember that this is 1.57 and this is pi, so 3.14, somewhere around there. So if you have 0.330, it's probably right around there. Okay, it's in the first quadrant. And that's not what we want. We want this to be in the third quadrant. Okay, so what we have to do is we have to add pi to it. So we're going to say plus pi. So our theta is actually equal to 3.472. Now, if it's easier for you to operate under degrees, that's fine. You could do that. So if you did degrees, I'll write the same things in here. When you first did this problem, you would have had theta equals, what was it? 18.925 degrees. And you'd be like, that's the wrong quadrant. So I'm going to add 180 degrees to put it in the third quadrant. So when you do that, you have 198.925 degrees. Okay, so you could do that as well. Just kind of look and see if I said put it in radians, put it in radians. If I said put it in degrees, put it in degrees. If I didn't say, I don't care. You can put it in either one. All right, so it says now that we know the basics about how to graph individual points, let's think about graphing polar coordinate equations using a t-table. Okay, so if I put this on a non-calculator test, this is how I would ask you to do it. It is kind of time-consuming, so I probably wouldn't put a lot of these, but these first two are pretty basic. So if you have r equals 2, that means if you do a t-table with r and theta, theta is the independent variable. This is what we're plugging in for. So I'm plugging in 0, I'm plugging in pi over 6, I'm plugging in pi over 4, pi over 3, pi over 2, and so on. You don't have to do everything between 0 and 2 pi, but you could do like every pi over 4 or just a few of them to see what's going on. But it says r is always equal to 2, so it doesn't matter what you're plugging in, you're always getting 2. So what happens is we have this point, and we have this point, and this point, and this point, and it goes around and it becomes this circle with radius 2. Okay, and then theta equals 3 pi over 4. That's kind of the same situation, but now the theta is what's constant. So theta is always 3 pi over 4. It doesn't matter what your radius is. Okay, so if theta is always 3 pi over 4, that means that we're always along this line. We have this point, and this point, and this point, and this point. But we also have negative values too, right? Like I could plug in -1, and I still get 3 pi over 4, so that would be right there. So we end up having a line that goes down like that. Okay, so now we get a little bit harder. So if we have something like r equals 3 sine theta, this is where it gets to be a little bit time consuming. So that's why I'm saying I wouldn't put a whole bunch of these on there. Okay, so let's try a few points. Okay, so let's say I plug in 0. We could do the pi over 6 and the pi over 4 and all of those points. But it does get to be a lot. So if you want to do maybe just a few of them, and then definitely do like the quadrantal angles, like the pi over 2 and the pi and 3 pi over 2. And let's see what happens. So if I plug in 0, I get 0. If I plug in pi over 6, I know that sine of pi over 6 is 1/2, so this is 3 over 2, so I'm going to write it as the decimal 1.5. All right, then if I plug in pi over 4, I get the decimal, you can do it as well, 2.121. If I plug in pi over 2, I get 3. If I plug in pi, I don't even think I did plug in pi, so sine of pi is 0, so I get 0, and so on. So 3 pi over 2, sine is -1, so -3. All right, so as I plot this out, I get 0, 0. And then along the pi over 6 line, so along this line right here, I go out 1.5. So 1.5 is going to be like right there. And then along the pi over 4 line, I go out 2 point something, so a little bit more than 2. And along the pi over 2, I go out 3. 1, 2, 3. And then I go out 0 along the pi line, and -3 along the 3 pi over 2. That puts me back here. So maybe I need to do some points that are over here. I feel like I'm missing some stuff over on this side. Okay, so that's when I would try some additional points to see what's going on. So maybe plug in, let's do 2 pi over 3 and 3 pi. Whoops, plugging in on the wrong side. It's hard when it's the independent variable, it's on the right. So 3 pi over 4 and 2 pi over 3. So if I plug in 3 pi over 4, I got, again, 2.121. And if I plugged in 2 pi over 3, I got 2.598. So maybe that's going to help me. So I have 2.121, and it ends up being kind of symmetric with that other one on the right-hand side. And then 2.522, so a little bit bigger. Okay, and you can try some other points. It ends up being symmetric with the other one. So what's happening is it's going around like this. And it becomes a little tiny circle that's right there. Okay, so like I said, it does take a little bit of work. If I was asking for specific points and it was a hard one, I would probably let you use your calculator. So I'm going to show you what this looks like. So if you have 3 sine of theta, okay, we're going to go to mode. Oh gosh, it never lets me do this right away when I open it up again. Okay, so we're going to go to mode, and we're going to put it in polar coordinates. So hit enter where it says polar, and let's make sure we're in radians. And then we're going to go to y equals, and now everything's in terms of r. So I'm going to put 3 and then sine. Whoops, I always do that. I always try to type sine. It does not like that. I'm going to delete it out. That's just clear. So I have 3, and then I have sine of theta. I'm going to hit graph. And you can see it's a little, kind of like a little circle there. And then I do second, and if you go to table, you want to be able to put in whatever values you want. So you might have to adjust your calculator, so you're going to do second table set, and you want to make it so your independent is whatever you want. So hit ask, and then enter. And then second table, so go back, and now you can put in whatever you want. So this is when I would put in like 0. I would put in pi over 6. So second, this is going to take forever to click. So pi divided by 6. And then I would put in, you know, pi over 4. And put in several different values just so you have the decimal approximation to help you sketch that out. Okay, so I don't know exactly if I'll put this on the calculator or the non-calculator. It is a lot to do without a calculator. So those first 2 examples were really easy, but this one's a little bit harder. So I kind of understand. I mean, hopefully you can do it by hand, but it's kind of time consuming for a test. All right, so let's try the next one. So for the next one, we have 2 cosine theta. So we're going to do 2 and then cosine theta. I still have my theta, so I'm going to hit graph. So it looks like it's also a little tiny circle on its side, or off to the right of the pole. So I'm going to do the second table, and I'm going to put in different values. So I've already actually put in these values for you, so I'm going to go ahead and put them on the notes. All right, so if I do r and theta, and I start plugging in different values for theta, so like 0, pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3, and 3 pi over 4. And you could go on if you wanted to. You have 2, 1.73, 1.41, 1, 0, -1, -1.414. All right, so I'm going to have 2, 0. Along the pi over 6, I'm going to go out 1.73. Along the pi over 4, I'm going to go out 1.41. So see, I'm getting a little bit closer to the full. Pi over 4, I'm going to have 1. Or not pi over 4. Pi over 3, I'm going to have 1. It's getting very close. 0, I'm going to have pi over 2. So it's back at the pole. And then I have, or pi over 2, I have 1. Or 0, I mean. 2 pi over 3, I have -1. So 2 pi over 3 is the line right here. So I'm going to go back -1. And then 3 pi over 4, which is this line, I'm going to go back -1.4. And slowly and surely, you do get this little tiny circle there. Okay, so it does work out. All right, so on the next part of the notes, I have lots of little investigation problems for you. I want you to really play around with your calculator to see what you get. So I went ahead and graphed these in for you. So you don't have to copy every single one of these, but I want you to really, really play around with the calculator. So let me show you a couple examples. So let's say I do, here's my little thing here. Let's say I go to y equals, and I do 4 cosine of 3 theta. Okay, and I hit graph. Okay, notice how I have 3 little petals. Okay, if I go to my y equals and I change that 3 and I make it 4, and then I hit graph, I now have 8 different petals. Okay, so you can count them, there's 8 there. So it's like, what's the pattern here? All right, so if I try 5 and hit graph, I'm back to 5 petals. And if you notice, they are going out a distance of 4, which was that first number that I had, the 4 there. So if I made that a 2, for instance, if I hit graph, it's a little bit smaller, okay? Or if I made it, let's make it 10. So second insert, so 10, and then I hit graph. Right, then it's really big. All right, so if you're noticing that whenever you have an even number, like if I put a 2 there and I hit graph, I'm going to have 4 petals. Okay, but if I put an odd number, like if I go to 3 and I hit graph, I have the same number. Okay, so whenever you have an even number, these are called the rose curves because they make little flowers, the rose curves. Whenever you have an even number, you end up with, what did we say? If we have an even number, we end up with double the number of petals. And if we have an odd number, we end up with exactly the same number of petals. Okay, so those are going to be the rose curves that we just did. So those are the ones above there. So you might want to do like a little arrow to the other page or whatever. All right, so then we're going to try the next ones. And I actually made a typo on the next ones. So please fix this for me. These should be negatives in front. So make all of those negatives. And then it's also going to be in the little box. It's going to have the negatives there. So I was graphing it and I was like, this is not what I thought this looked like. And then I realized I made a typo on all of those. Okay, and these are actually going to look like infinity signs. So what we're going to do is we'll go to our little graph and we're going to put in like -3 squared cosine of 2 theta. Okay, but I actually have to put a positive square root and a negative square root. So I'm going to do second square root of, and I'm going to do negative, let's make it bigger, 5 squared. And then I'm going to do, what did I have cosine first? Cosine of 2 theta. Okay, and then on the next one, I'm just going to do the negative square root. So the same thing of the -5 squared cosine 2 theta. Okay, so these ones are a little annoying to type out, a little bit longer. All right, and when we do that, we get like a little infinity sign. Okay, if you're having trouble getting these graphs, check your window. Notice how mine is 0 to 2 pi. So I had put in 2 pi there. And I made my step kind of small, okay, like 0.1 around there. If you want to go to 0 to 4 pi, what it's going to do is it's going to trace the curve twice, basically. So it's going to, if you continue to plug in those values, it's giving you the same output. So you can do that if you want to. All right, so the next ones we have involve like 3 plus 2 cosine theta. So let me go ahead and do that one. So I'm going to go to my y equals, and I'm going to clear these out. So I get the 3 plus 2 cosine theta. Okay, and it looks kind of funny. All right, but if I do, if I switch these and I do a 2 here and then a 3 here, it looks a little bit different. So see if you can tell the difference. Okay, and maybe you need to zoom in a little bit. You can hit zoom in as 2 and then hit enter. And you can see there's a little like loop in there. Okay, so I'm going to go back to my standard, so zoom 6. All right, so there's definitely something going on with that loop. So what if I change these numbers, and what if I do a 1 here and a 5 here? Okay, now when I hit graph, the loop's even bigger. And the thing that's important about these are these numbers right here. So if you notice this number right here, it is 6, and this other one's 4. Well, what does that have to do with 1 and 5? 1 is the sum of the two, and 1 is the difference of the two, right? So let's play around with it. Let's say we have 2 and 9. Okay, when we graph it, it goes out to 11. I guess it ran off the screen a little bit. I could change my window if I wanted to make my X max go to, let's say, 12. And then I could hit graph again so we can see it. So it goes out to 11, and then 9 minus 2 is 7. This point's at 7. Okay, so the ones where the number was bigger here and smaller here, they don't do that, though. They don't have that little inner loop, right? So this one looks almost flat, like almost like an ellipse, right? So what's happening with these is some of them have what we call an inner loop and some of them don't. So the last ones that we just did were the lemniscate. Lemniscates are the infinity signs. The ones that we're learning about now, these are called limacons. So limacons, it's very French, limaçon. Limacons sometimes have an inner loop and sometimes they don't. Okay, so if A is less than B, there's no inner loop. If A is greater than B, there is. Or if A is less than B, there is an inner loop. If A is greater than B, there is no loop. Okay, so if you're seeing something like 3 plus 7 cosine theta, what's going to happen is you're going to go out to 10, and then your inner loop is going to go into 4. So it's going to look something like, oops, like that, okay? All right, so those are called the limacons. And then there's a special form of limacons, which is called the cardioid. Cardioid makes you think of heart, right? Cardioid. So it looks kind of like a heart. It actually looks like the heart that's actually in our body. It's not pointy on the bottom, you know, like the way we draw hearts today. We have like these little points there. It's more like that. Okay, so these are cardioids that have this little shape. And this is a special case of a limacon. So it's still going to go out to the sum. Okay, but it's only going to go into 0. So all of these are going to be on the pole. And if you notice, if you played around with the last ones and you changed, instead of doing cosine, if you changed it to sine, they would have been vertical, right? The same thing for the cardioids. Cardioids are going to be vertical when you change to sine. All right, and then the last one we have are the ones where we just have like r equals theta, or r equals 2 theta, or something like that. And those ones actually make a spiral. So let me show you those. Oops, wrong thing. So if I go to my y equals, and I change this out to just r equals theta, and I hit graph, okay, it makes a little spiral. And that spiral can actually be bigger if on my window, instead of going to 2 pi, let's say I go to 10 pi. Okay, and then I hit graph. Okay, it's going to draw all the rest of the spiral. And I can adjust how tight the spiral is. So maybe if I want to insert and I put in like 0.5, okay, this is going to be like a tighter, a closer spiral. Okay, so it's looking like that. Pretty cool. Aren't you guys excited to be graphing these cool things on your calculators? All right, but if I put in, instead of 0.5, if I put in, let's say, just 5, okay, then it's going to be like more spread out, so you're not going to see a lot of the spiral. Okay, so that's how the spiral's adjusted. So the spiral's still there, it's just so big that you can't see it on the screen. So if I zoomed out several times, it says 3, and I hit enter. And then if I hit enter again, it would zoom out. Well, I guess I have to do it again. It says zoom. Oh, it's still thinking. It's thinking really hard on here. Okay, so anyway, so you could zoom out and you could see more and more of that spiral if you wanted to. Okay, so those are the different section polar coordinate sketches. So there's really cool things that you can graph on your calculator. Like I said, I'm going to continue this section in a second part. So you can start the Math Excel homework if you want to, but when it comes to converting from polar to rectangular, we haven't done that yet. So you might want to pause the Math Excel and then watch the second part of the video. So like I said at the very beginning, this is kind of the longest section in summer pre-calc. I will make sure that I break it up next time I teach this class. All right, thanks.